Alright, so in this video I'm going to use the data to look at kinetics, and in this case we're going to be looking at basically a set of experiments. You can see listed here experiments 1 through 5, where we're trying to solve for the rate law and the rate constant given a set of initial concentrations and the associated initial rates. So taking a look at this chart quickly, just to identify here, we've got our experiment listed, concentration of reactant A, concentration of reactant B, and then the initial rate in molarity per minute. Keep in mind you have to use initial rates for this kind because over time, again, you're going to get towards equilibrium. The net rate that you can absorb will change with the concentration. Okay, for that we need to use the integrated rate laws, which we'll do another video on using linear fits for those. Okay, for now I'm going to start off by just writing the generic rate law, which is that rate is going to be equal to K, concentration of A to some power, call it M, concentration of B to some power, we'll call it N. And the first thing we're going to have to do pretty much is figure out what is M and what is N. So in doing that, okay, I'm going to have to pick some experiments here. The first one I'm going to do is look at experiment 1 and experiment 3. If you look at experiment 1, concentration of A is 0.5, experiment 3, concentration of A is 1, and so what we can do is we can simply look at the relationship between the two of those. If you notice, we've essentially doubled the concentration of A, so between experiment 1 and 3, we double concentration of A, and what we're really looking now is to figure out, well, what happens to the rate. Well, when we double the concentration of A, the rate goes, I'm going to put the second one over the first here, so 34 times 10 to the negative third over 8.5 times 10 to the negative third, and that's going to be equal to 4. So when I double A, the rate is 4 times higher. Okay, the constant that therefore tells us that we're going to be second order with respect to A, or it's squared, right? So we know now that M is going to be 2, so we can write this as rate equals K times concentration of A squared, and now we need to figure out B. So I'm going to take a look at experiment 1 and 5. Okay, if you look initially, concentration of A is 0.5 and 1, it's 0.5 and 5, so it hasn't changed at all, but the concentration of B has doubled. So B is twice as big in experiment 5 as experiment 1, so we're doing the same type of thing here. We're doubling the concentration of B. Right, and therefore the rate will need to be compared between experiment 5 and experiment 1. And experiment 5, it's 8.5 times 10 to the negative third. Experiment 1, it's 8.5 times 10 to the negative third. Okay, so that ratio is 1. So when we double B, the rate is still 1. That means that B is not involved. So N is 0. It's 0 order with respect to B. So that'll be to 0. So our rate law is just rate equals K times concentration of A squared. Therefore, if we want to find out the rate constant, all we need to do is plug in one of these experiments and solve for K. So we'll just use experiment 1 here and say 8.5 times 10 to the negative third molarity per minute is equal to K times concentration of A, 0.50 molar squared. Okay, we're going to divide both sides by 0.50 molar squared, so by 0.25 molar squared, and what we're going to get is K is equal to 0.034. That'll be molarity to the minus 1 and minutes to the minus 1. So we have our K value now, and we know that our rate law, so rate is equal to 0.034 molarity to the minus 1 minutes to the minus 1 times concentration of A squared.